In this course, we are going to build a complete production-ready e-commerce application using ASP.NET Core and .NET 10. Starting from an empty solution, we will design a clean architecture, implement a solution, and secure a RESTful web API, and connect it to a real database using Entity Framework Core. You will learn how authentication, business logic, data access, and validation all work together in a modern backend system. By the end of this course, you will have a complete backend project that you can deploy, and you will have the capacity to think like a senior developer, starting your projects from scratch, starting new system design, starting your own architecture that replies to your needs in your project. In this project, we are going to build the complete e-commerce backend application from the ground up using ASP.NET Core and .NET 10. That means creating a system that manages products, categories, shopping carts, and customer orders. We will design a clean architecture, implement secure authentication, handle data with Entity Framework Core, and expose everything through a professional RESTful API. Alright, let's start from the very beginning. I'm going to create a new project using Visual Studio. So I will open Visual Studio, click on Create New Project, and here we are going to select ASP.NET Core Web API because we want to build a backend API that exposes endpoints. I will click Next, give the project a meaningful name, something like ecommerce.api. Choose a location on your machine and keep the solution name consistent so everything stays organized. Click Next. I will make sure that the framework is set to .NET 10. Enable Open API support so we can get Swagger for testing, and for this project leave authentication as none because we will implement our own later from scratch. I will also keep controllers enabled instead of minimal APIs since the structure is closer to real production applications. Then I will click Create and Visual Studio will generate the base project for us. What you are seeing now is a default template working web API with example files. Don't worry if you don't understand what these files really do. It's just a starting point. In the next steps, we will clean up all of this and begin shaping into a real e-commerce application. Now the project is created. Let's take a moment to understand what Visual Studio generated for us. On the right side in Solution Explorer, you can see the structure of this project. The most important file is program.cs. This is basically the entry point for our application where the web server is configured and all services are registered. In modern .NET projects, most of the startup logic lives right here. You will also notice a controller folder. This is where our API endpoints will live. Inside there is a sample controller that Visual Studio created just to prove everything is working. We won't use it in the real project, but it's helpful for testing. Now inside the properties folder and inside the launcher setting JSON, all you need to do is to set the property launcher browser equal to true. Now every time we hit the run button, a new web browser page will be automatically opened. But before that, make sure that the e-commerce API project is set to startup project. Now inside the program CS, we need to set up Swagger so we can add the endpoint APIs Explorer. Then we can add the Swagger, so builder services, add Swagger, and here we can find Swagger on the packages list. So inside the NuGet packages, let's add a new NuGet package. Okay, and here inside the program CS, we can add the Swagger gen. One last update inside the environment, we can add app.use Swagger, and you can add another one for use Swagger UI. If we run the application now using the green start button, the browser opens automatically to Swagger, and if not, you can just add Swagger. Okay, and now you can see all the default configuration made by the ASP.NET. So at this point, we have a fully working ASP.NET Core Web API project. Nothing fancy yet, but a solid foundation. Now that Swagger is configured and our application is running properly, the next thing we want to do is to clean up the default template. Visual Studio generates a sample controller, usually something like Weather Forest controller, which is useful for testing but not relevant for our e-commerce application. Since we are building everything from scratch, I'm going to delete this file, and I'm going to delete the weather forecast. This just it's a business logic. That's a file that contains some properties. The next step is to create our first real controller. Inside the controllers folder, let's add a new controller, API, empty controller, because we want a full control instead of a generated template. I will name it products. I will name it products controller. Inside the controller, we will add the basic attributes that make a proper Web API controller. The API controller attribute for automatic validation and behavior, and route API controller to define how clients will reach this endpoint. For now, I will create a simple get method that returns a placeholder list of products just to confirm everything is wired correct. If we run the application again and open Swagger, you should now see the new products endpoint appear. If you want to test it, click on the button execute, and you can see the list of products we already set up inside the controller. That's our first real piece of functionality. Small step, but this is exactly how real APIs grow, one resource at a time. The next step is to replace the hard-coded sample data with a proper model that represents a real product. In real applications, we don't return anonymous object, we define clear classes, so the structure is consistent, reusable, and easy to maintain. So I'm going to create a new folder inside the project, add a new folder and call it models. And inside the models folder, let's create a new item and call it product. This class will maintain the core properties of products such as ID, name, description, price, and stock. Once the model is created, we will update our controller to return a list of product objects instead of anonymous data. Functionally, it will behave the same for now, but architecturally, it's a big improvement because we are starting to build a real domain model. Later, this class will be used inside the application and will be mapped with the database and will be used throughout all the application. After making these changes, let's run the application again and verify inside Swagger if we got all we need. So inside Swagger, try it out, execute, and now the result returns structured product objects. Now we can retrieve all products. The next logical step is to allow clients to request a single product by its ID. This is a very common pattern in RESTful APIs where each resource can be accessed individually using its ID. So inside the same controller, we are going to add another GET endpoint that accepts an ID as a route parameter. We will use an HTTP GET ID attribute which tell the ASP.NET Core to match URLs like API products 1. Inside the method, we will search in our memory list if any of the products match the product with the ID. So if it exists, we will return a 200 response that the element exists, and we will show it via Swagger. Else, return a not found result. After adding the endpoint, we can now run the application and check via Swagger. So we need to update the URI. And here you can see that we have an API products ID. And if we want to try it, we can 2, for example, and execute. And the result is return the products with ID equal to 2, the headphones. So all is working very good. This is it for the first part. So today we creating a new solution. So this task is done and we configured Swagger too. We started defining the endpoints. It's not completed. We just worked with the get all products and get only one product. It's not yet finished. So in the next tutorial, we are going to work with the put, with the delete, and with the post. And we are going to create the DB context, a repository design pattern, and defining some relation between the entities. So don't forget to subscribe. The series is going to be huge, very long series, so about 12 hours. So stay tuned and subscribe to the channel. See you in the next video. Now let's allow clients to create new products. In RESTful APIs, this is done using a post request. I'm going to add new method to create it with the post attribute, which means this endpoint will respond to post requests sent to API/products. The product data will come from the request body as JSON, and ASP.NET Core will automatically convert it into our product object. Since we don't have a database yet, I will simulate persistence by assigning a random ID and setting the creation timestamp. Instead of using a simple OK response, I'm using created at action. This returns 201 created status code and included the location of the newly created resource, which the correct behavior for a RESTful API. Now if you run the application and open Swagger, you can send a post request with the product data and see the API respond to the created object. This is our first step toward a full CRUD functionality. Now that we can create products, the next step is to allow clients to update an existing one. In RESTful APIs, updates are typically handled using a put request. This means the client sends the product ID in the URL and the updated data in the request body. So I'm adding a new method created with the HTTP put ID, which tells the ASP.NET Core to match the URLs like API products 1. The framework will automatically bind the JSON payload to our product object. Then, since we are still using the simulated data, I will search our in-memory list for the product with the specified ID. If the product doesn't exist, we return a 404 not found, which is the correct response when trying to update something that isn't there. If it does exist, we simply update its properties with the new values provided by the client and return the updated product with the 200 OK response. After running the application, you can test this endpoint in Swagger by providing an ID and sending updated product data. This brings us one step closer to full CRUD functionality, where clients can create, read, update, and eventually delete resources just like a real-world system. Now that we can create and update products, the final operation we need for full CRUD functionality is the ability to delete a product. In RESTful APIs, deletion are handled using the delete HTTP method. I'm going to add new endpoint to create it with HTTP delete ID, which means it will respond to requests like API/products/1. The ID in the URL tells the API which product should be removed. Inside the method, we again search our simulated data for product with the specified ID. If no matching product is found, we return a 404 not found, because the client is trying to delete something that doesn't exist. If the product is found, we remove it from the collection. Instead of returning data, we return a 204 no content response. This is the standard REST behavior for successful deletion. It confirms the operation succeeded but doesn't send anything back to the response body. After running the application, you can test the Swagger by providing an ID. So the delete, we can add an ID from the list, try it out. For example, we can add work with the ID equal to 2 and execute. And here you can find that the code status returned is 204. We can test with an element that doesn't exist on the list, for example, ID equal to 10, and execute. And you can see here that we have a response of 404. Now we have completed another task, is the CRUD operations. For the next step, we are going to work with the entity framework, creating a DB context, define the relationships between entities, add migrations, and seed initial data so we can add elements to the database. So far, our API looks functional, but there is one major limitation. All the data is stored in memory. Every time we restart the application, everything disappears. In real-world systems, data must be persistent, which means we need a database. In this step, we are going to integrate SQL database using Entity Framework Core, which is the official object rational mapper for .NET. Entity Framework will allow us to work with our database using C# classes instead of writing raw SQL, making development faster and more maintainable. We will start by installing the required Entity Framework packages. NuGet packages, and here we need to use the Entity Framework Core .SQL Server. Hit install. Once it's done, let's install the second one. Now let's add new folder, call it data. And inside this new folder, let's add a new item. And this item is going to be for the app DB context. And now let's add a constructor ctor, and this constructor, let's inject the dependencies. We need db context options, update the context, and we call it options. And this is deriving from the base options. And now let's add a new db set for our first table, product. So every db set we add here is a real table on the database. We call it products with a lambda expression of type product. Let's save. Now let's go to the app setting and let's set a connection string. I'm creating a new database called e-commerce app with the server local DB. Now we have created the app DB context and configured the connection string on the app setting. Let's go to the program CS and register the DB context. All we need to do is builder dot services dot add DB context. Then the name of the DB context, it's app DB context. You need to use the same name you used here. And we need to use the options. Options.use SQL server, and here we need to use the builder dot configuration dot get connection string, and inside the app setting we name it default connection. We need to use the same name here. And save. So before we proceed to create our database, all we need is to move this line before the builder, before we build our application, and we need to make a little modification for the decimal value here, because decimal makes some ambiguity when creating the column inside the database. So all we need to do is to add a property for this one. It's going to be very simple. So column type name, and it's going to be a decimal with 18 digits and 2 decimals. Let's save. And now inside the package manager console, all you need to do is add migration initial create. So build is succeeded and all is good. And here you can see that a new folder has been created called in migration that contains the migration and contains all the column inside the product table. Now if you look inside the SQL server, you can't find the database because it's not created yet. Inside the Visual Studio we need to run another command line. It's update database. Now inside the SQL server we can refresh for the databases, and you can see that a new database has been added, e-commerce app, that contains only one table, and this table contains all the columns we already defined inside the product entity. In the second part we added migrations, so this task is done. We have created the database. The next tutorial we are going to define the relationships and seed initial data. That means adding data to the database. Now that our database is configured and the products table has been created, the next step is to use it inside our API. Up to this point, all of our endpoints were working with hard-coded in-memory data, which means nothing was being stored permanently. In real applications, controller communicate with the database through Entity Framework core. So we are going to replace that fake data with the real database operations. To do that, we inject our app.db context into the controller using dependency injection. ASP.NET Core will automatically provide an instance for us because we registered it earlier in the service container. Once injected, we can use it to query and modify the products table using link, just like working with normal C# collections. We will start by updating the get endpoint to retrieve products directly from the database. After that, we will modify the post, put and delete endpoints to persist changes so that data remains even after starting the application. This step transforms our API from a prototype into a real data-driven backend. You may notice that our controller methods now use async and await. This allows the API to perform database operations without blocking the thread, which improves scalability and performance, especially when handling many requests at the same time. Entity Framework Core provides asynchronous methods like toListAsync and findAsync, so we use them to keep our application responsive and efficient. For now, just know that this is the recommended way to work with databases and modern ASP.NET applications. Our API has been sending and receiving product entities directly. While this works, it's not recommended for real applications. Entities represent our database structure, and exposing them directly can create security risks that make the API harder to evolve over time. Instead, we introduce data transfer objects, or DTOs. DTOs define exactly what data is exchanged between the client and the server, allowing us to hide internal fields, validate input more safely, and keep the API contract stable even if the database changes. We will create separate DTOs for reading and creating products. The controller will convert between DTOs and entities before creating and interacting with the database. This extra layer may seem small, but it's a key step toward a clean production-ready architecture used in professional systems. For a start, inside the Explorer, let's add a new folder and let's call it DTOs. Inside the folder, let's add a new item and call it product DTO. So the DTO is a security layer above the product, so we need to copy this and paste it inside the product DTO. We get rid of this, we don't need this, we don't need the created at, and let's save. Now let's create another DTO for the creation, so we call it create product DTO, and we need to paste all the properties. We don't need the ID because it's going to be used for the creation. We delete this and we delete the create at and save the file. Now we need to create another DTO for the creation, so let's add a new item, call it create product DTO. We need to paste all the properties. We don't need an ID because it's going to be used for the creation. We don't need this, and we don't need the created at, and save the file. Now that our DTOs are defined, the next step is to update the controller so it no longer exposes the product entities directly. Instead, the API will receive and return DTOs while the database continues to work with entities internally. For read operations, we will fetch products from the database and map them to product DTO objects before returning them to the client. For create operations, the API will accept a create product DTO, convert it into a product entity, and then save it to the database. In a production system, create and update operation often use different DTOs because the validation rules may differ. However, for simplicity at this stage, we will use the same DTO for both creating and updating products. Later in the series, if we need more control for the DTO, we can introduce a dedicated update DTO. Now that all CRUD endpoints are implemented, the next step is to verify that everything works correctly with the real database. I will open Swagger, which provides an interactive interface for testing our API without needing front-end application. First, I will create a new product using the post endpoint and check if it appears both in Swagger and the database. So let's start with the post, and here we can try it. We can copy this. The name, for example, it's going to be laptop. Description. And for the price, 20 for the stock. Now let's execute. And here for the status, 201, that's mean new line has been added to the database, and so we can verify inside the database directly. And we can see that the high performance PC already added now. After that, we can make another test for the get, and we know that the ID is 0. We can check that in the database, so ID equals to 0. We can try it. And here we got our PC already created. For the boot, we can just copy this because we're going to need this inside the boot. Try it. 0, we don't need the ID, but for the name we can say something like updated laptop. Execute. Code status 200 updated laptop, and if we verify inside the database, so it was laptop and now updated laptop. That's mean our API is working very well. And now for the last endpoint, try it, and we say 0, execute. Code status okay, and inside the database the element is deleted. So we have done with the tests, and this validation step is crucial because it proves that our API is not just returning mock data, but it's performing a real database operations and maintaining persistent state across the requests. So in this video we defined the endpoint for the product controller. We used the async await on the product controller. It was not very detailed, but I think I'm going to make a new video for all the details with multi-threading for async and await. We mapped the DTOs into entities for the creation and getting the DTOs from the product controller. We created the request DTOs, and we created the product API. So all the endpoints, the get, the update, the put, and the delete. See you in the next tutorial. In this part, we are going to make API more robust by adding validations. Right now, our application accepts any data sent by the client, which can lead to invalid or inconsistent data being stored in the database. To fix this, we will use data annotation in ASP.NET Core to define validation rules directly in our model. The best part is that thanks to the API controller attribute, validation will be handled automatically by the framework. First, we need to import the necessary namespaces. The data annotations namespace provides validations attribute like required, max length, and range. We also keep the schema namespace because we are defining how the decimal field is stored in the database. The ID property is the primary key of our table. It will be generated automatically by the database, so we don't need to validate it. For the name property, we need to add validation rules. Required ensures that the client must provide a value, and max length limits the size of the text to 100 characters. This prevents empty or overly blocked product names. For description, we don't make it required, but we still limit its length to 500 characters. This keeps our data clean and avoids unnecessary large inputs. For prices, we ensure that the value is within a valid range using the range attribute. This prevents the negative or zero prices. We also explicitly define the SQL column type as decimal with precision, which is very important when working with money to avoid rounding issues. For stock, we make sure that the value cannot be negative. A product can have a zero stock, but never less than that. The created at property is automatically set to the current UTC time when a product is created. This allows us to track when each record was created without requiring any input from the client. Now our product model is properly validated. Any invalid data sent to the API will automatically be rejected with a 400 bad request response. In the next step, we will test these validation rules using Swagger and how ASP.NET Core handles invalid input in real time. Since we already separated our API into DTOs, it makes more sense to validate input where it actually enters the system. The create product DTO represents data coming from the client. So this is where we should enforce rules like required fields and valid ranges. Now let's test our validation rules directly from Swagger. So let's start the application and let's go to Swagger, and I will open the post endpoint for creating product. I will click on try it out, and here I will give an empty string. So execute, and here we got a 400 status. The name field is required. So when I execute the request, ASP.NET automatically checks the validation attributes we added to the DTO. Since the name field is required, the request should be rejected before it reaches our database logic. So the API returns a 400 bad request response, which means the input is invalid. Swagger also shows the validation error details, so the client knows exactly what needs to be fixed. In this tutorial, we covered how to implement validations. So this task is already done. In the next tutorial, we can work on the error response format, or we can even add more entities, or we can create the Git repository. So don't forget to subscribe, and see you on the next tutorial. In the last video, we added validation using data annotation directly in our DTOs. While that approach works, it has some limitations. As application grows, validation logic can become harder to maintain, harder to test, and tightly coupled to our data models. In this video, we are going to take things to the next level by introducing fluent validation. This is a powerful and flexible library that allows us to define validation rules in a clean, readable, and maintainable way. Instead of putting validation attributes on our DTOs, we will move that logic into dedicated validator classes. By the end of this video, you will understand why fluent validation is widely used in production systems, and you will be able to apply in your own ASP.NET Core applications. Let's start by installing Fluent Validation into our project. This package will allow us to define validation rules outside of our models. In Visual Studio, open NuGet Package Manager and search for fluentvalidation.asp.NET Core. Then install it. This package integrates Fluent Validation directly into the ASP.NET Core pipeline. Once installed, we are ready to start creating validators. Now, instead of placing validation attributes inside our DTOs, we create a new dedicated validator class. This class inherits from abstract validator and is strongly typed to create product DTO. This means all validation rules defined here and will apply specifically to this DTO. This separation makes our code cleaner and easier to maintain. We start by defining validation rules for the name field. Using rule 4, we specify the property we want to validate. Then we chain rules together. Not empty ensures that the field is not empty, and maximum length limits is to 100 characters. Compared to data annotations, this syntax is more readable and expressive. Next, we validate the description field. This field is optional, so we don't require it, but we still limit its length. This ensures that even optional data remains controlled and consistent. For the price, we ensure that the value is greater than 0. Fluent validation gives us a very natural way to express this rule, making the content immediately clear. For stock, we allow 0 but prevent negative values. Again, the rule is simple and easy to read. Now we need to register Fluent validation in our application. This line scans the assembly and automatically registers all validators. This means ASP.NET Core will automatically use the validators whenever a request is received. At this point, we can remove all the validation attributes from our DTO. This is an important step because we want all validation logic to be handled in one place. By doing this, we achieve better separation of concerns. Our DTO now only represents data and our validator handles the rules. Now let's test our validation. So I will open post endpoint. It's here inside Swagger. So I will open the post endpoint, click on try it out, and inside of this I'm going to add an empty name and execute. And here we have a problem. So as expected, the API returns a 400 bad request response. The validation errors are clearly displayed, showing exactly what went wrong. So the status is 400. This confirms that the Fluent validation is working and correctly integrated into our pipeline. Compared to data annotations, Fluent validation gives us several advantages. First, it keeps validation logic separate from our models. Second, it allows us to write more complex rules, including conditional validation and custom logic. It also improves testability, since validators can be tested independently without needing the entire application to run. This makes the preferred choice in professional and production applications. Now our API uses Fluent validation for handling all input validation in a clean and maintainable way. In the next video, we will continue improving our architecture by introducing AutoMapper, which will help us simplify the mapping between DTOs and entities. So this task is done, the Fluent validation. The next time we can work with the AutoMapper. Don't forget to subscribe. In this part, we are going to clean up our controller by introducing AutoMapper. Right now, our API works correctly. You will notice that we are manually converting product entities into product DTO objects and create product DTO objects into product entities. This works, but as the application grows, this mapping code becomes repetitive and makes the controller harder to read. AutoMapper solves this problem by moving mapping rules into a dedicated profile. Instead of writing the same property assignment again and again, we define the mapping once, then reuse it everywhere. This keeps our controller focused on handling HTTP requests while AutoMapper handles object transformation. First, we need to install AutoMapper integration package for ASP.NET Core. This package allows us to register AutoMapper in the dependency injection container, so we can inject it directly into our controllers and services. Now we create a new folder called Mappings. and inside it we add a product profile class. In AutoMapper, a profile is where we define how an object should be converted into another. This class inherits from profile, which comes from AutoMapper. Inside the constructor, we define our mapping rules. The first rule maps product to product DTO. This is used when we retrieve data from the database and return it to the client. The second rule maps create product DTO to product. This is used when the client sends data to create or update product, and we need to convert that input DTO into our database entity. Because the property names are the same, name, description, price, and stock, AutoMapper can match them automatically. After creating the profile, we need to register AutoMapper in program.cs. This tells ASP.NET Core where to find our mapping configuration. We pass the product profile type to add AutoMapper, and AutoMapper will scan the assembly and register the mappings defined in the profile. This must be done before build.build because services and service registration happens before the application is built. Next, we inject IMapper into the controller. Just like AppDB context, AutoMapper is now registered in the dependency injection container, so ASP.NET Core now can provide it automatically. We store it in a private read-only field called mapper. From now on, whenever we need to convert one object into another, we will use the mapper instead of writing manual property assignments. Let's start with the getAllProducts endpoint. After retrieving the products from the database, we used select and manually created new product DTO for each product. That worked, but it added extra mapping code inside the controller. Now we replaced that with only one line, mapper.map, and we are going to use the IEnumerable products. This tells AutoMapper to convert the list of product entities into a list of product DTO object using the mapping rule we defined earlier. For the getProductById endpoint, the logic stays almost the same. We still search the product using the find async, and we still return not found if the product does not exist. The only difference is the mapping step. Instead of manually assigning ID, name, description, price, and stock, we simply call mapper.map product. This makes the endpoint shorter and easier to understand. Now let's update the post endpoint. When the client sends us the create product DTO, we need to convert it into a product entity before saving it to the database. Earlier, we created a new product manually and copied every property one by one. Now AutoMapper does that for us using the mapper.map. After saving the product, the database generates the ID. Then we map the saved product entity back into the product DTO and return it using the created add action. This keeps the endpoint focused and on the workflow, receive input, map it, save it, and return the response. The put endpoint is slightly different because we are updating an existing product. First, we retrieve the product from the database. If it does not exist, we return not found. Then we use the mapper. This means AutoMapper will copy the values from the DTO into the existing product entity. This is important because we are not creating a new product here. We are updating the tracked entity that entity framework already loaded from the database. Once we call save changes async, entity framework core detects the changes and updates the record. The delete endpoint does not need AutoMapper because we are not converting data. We only need the product ID, then we find entity, remove it from the database context, and save the changes. So AutoMapper is useful when we transfer objects, but not for deleting operations. There is no DTO mapping required. At this point, our controller is much cleaner. We removed the repetitive mapping code and moved the mapping rules into the dedicated AutoMapper profile. This makes the project easier to maintain and closer to how real production APIs are structured. In the next part, we can continue improving the project by adding a service layer, for example, and for the controller does not communicate directly with the database anymore. That will help us separate HTTP logic from business logic and make the application easier to test and scale. So for the AutoMapper task is done. The next tutorial we can implement the service logic to add more production features to our project. Don't forget to subscribe. So far, our products controller is working correctly. It can retrieve products, create new products, updating existing products, delete products, validate incoming data, and use AutoMapper to convert between entities and DTOs. But there is still one architectural problem. The controller is doing too much. Right now, the controller is responsible for handling HTTP requests, talking directly to the entity framework core, saving data to the database, and mapping objects. For a small demo, this is acceptable, but in real production application, this becomes harder to maintain. In this part, we are going to introduce a service layer. The goal of the service layer is to move to the first we create a new folder called services. This folder will contain the classes responsible for application logic. Inside it, I will also create an interfaces folder. This is where we will define contracts for our services. The reason we use an interface is to decouple the controller from the concrete implementation. Instead of the controller depending directly on the product services, it will depend on the iProduct service. This makes the code easier to test, easier to replace, and closer to a real-world dependency injection practices. Now we define the iProduct service interface. This interface represents the operations our product service must provide. We start with getAllProducts async, which returns all products as product DTO objects. Then we have getProductById async, which returns a single product by its ID. Note that this method returns product DTO with a question mark, meaning it can return null if the product does not exist. Next, we define createProductAsync, which accepts a createProduct DTO and returns the created product DTO. Then we define updateProductAsync, which also accepts an ID and a DTO. It returns a product DTO if the product exists, or null if it does not. Finally, deleteProductAsync returns a boolean. If the product was found and deleted, it returns true. If the product does not exist, it returns false. At this point, this interface defines what the service can do, but now how to use it, so let's see the implementation. Now we create the product service class. This class implements iProduct service, which means it must provide the methods defined in the interface. Inside the service, we inject appdb context and imapper. Appdb context gives us access to the database through entity framework core, and imapper allows us to convert between product DTO, and create product DTO. The important thing here is that the controller will no longer deal directly with the database. That responsibility now belongs to the service layer. Let's start with getAllProductsAsync. This method retrieves all products from the database using entity framework core. Because database call can take time, we use toListAsync and await the result. Once we get the list of product entities, we use AutoMapper to convert them into product DTO objects. This means the service returns data in the format expected by the API response, without exposing the database entity directly. Next, we have getProductById async. This method receives an ID and searches the database for matching product. If no product is found, we will return null. We do not return not found here because this is not the controller. The service does not know about HTTP responses. If the product exists, we map it to product DTO and return it. For createProductAsync, the service receives createProduct DTO from the controller. This DTO represents the data sent by the client. We use AutoMapper to convert the DTO into a product entity. Then we add the entity to the products table and call SaveChangesAsync to persist it in the database. After saving, entity framework core updates the product object with the generated ID. And finally, we map the saved product entity back into a product DTO and return it. For updated product async, we first retrieve the existing product from the database. This is important because we need to update a tracked entity, not create a new one. If the product does not exist, we will return null. Again, the service does not return HTTP responses. It only returns a result that the controller can understand. If the product exists, we use AutoMapper to copy the values from the DTO into the existing product entity. Then we call save changes. Entity framework core detects the updated values and generates the SQL update behind the scenes. Finally, we return the updated product as product DTO. For delete product async, we search for the product using its ID. If it does not exist, we return false. If the product exists, we remove it from the DB context and save the changes. After the deletion succeeds, we return true. Returning a boolean keeps the service simple. The controller can then decide whether false means not found or true means no content. Now we have created the service and its interface. We need to register them in the dependency injection container. So we are going to use an add scope because the service depends on app DB context, and DB context is also scoped by default. This means one instance of product service will be created per request. Now inside the controller, we remove app DB context and AutoMapper from the controller completely. The controller no longer knows how products are stored or how mapping is done. So it only depends on iProduct service. Now let's run the app, and via Swagger let's try to test all the endpoints. So we start with Swagger, we start with try it, get all the products. So we have 6 products. We can add a new one, so it's going to be a phone. Price is 900 and we have 12. Execute. So it's added with the ID 8, and now let's try it out and let's get the element with ID 8, and we got the phone we already created. And now let's update it. So we update the element 8, and let's update, let's remove the ID, and let's update the stock. Execute. So we have this, and now let's delete the element with the ID 8. Execute. The element is deleted, and when we run get all the elements again, we see that the element with ID 8 is deleted. Don't forget to subscribe. On the next tutorial, we are going to work with the global exception handler. Right now, if something unexpected happens in our application, ASP.NET Core can return a long technical error page in development or a generic error response in production. That's not ideal for a real API. Clients need clean, predictable JSON responses, and we also want a central place to handle errors instead of writing try-catch blocks everywhere. To solve this problem, we are going to create a custom exception handling middleware. This middleware will catch and handle exception globally, log the errors, and return a consistent JSON response to the client. First, we create a new folder called middleware. Middleware is code that runs as a part of the HTTP request pipeline. Every request passes through the pipeline, so middleware is the perfect place to handle cross-cutting concerns like logging, authentication, validation, and exception handling. Inside the folder, we create a new class called exception handling middleware. This class will be responsible for catching exceptions globally. Before writing the middleware, we create a small response model called API error response. This class is defined to shape the error response returned by our API. It contains a status code, a message, and an optional details. The status code tells the client what type of error happened. The message gives a clean explanation. Details can be used in development to show technical information, but we should avoid exposing sensitive details in production. Now let's create the middleware class. The first dependency is the request delegate. This represents the next middleware in the pipeline. Our middleware receives the request, then passes it forward by calling next. The second dependency is iLogger. We use this to log exception on the server side. This is very important because the client should not receive technical details, but developers still need to see what went wrong. The third dependency is iWeb host environment. This allows us to check whether the application is running in development or in production. In development, we can return exception details to help debugging. In production, we hide those details for security reasons. The invoke method is the core of the middleware. Every request that reaches this middleware will execute this method. Inside it, we wrap the rest of the pipeline inside a try-catch block. If everything works correctly, the request continues normally by calling next. But if any unhandled exception happens later in the pipeline, for example inside the controller or service, the catch block will capture the problem and send it to our handle exception async method. This means we no longer need to put a try catch block inside every controller action. The first thing we need to do when an exception is caught is log it. This is very important because the server should keep the full technical details of the error. Even if we return a clean response to the client, developers still need the full stack trace in logs to debug the issue. Next, we configure the HTTP response. Since this is an API, we want to return JSON, so we set the content type of application to application JSON. Then we set the status code to 500 internal server error. The status code means that something unexpected happened on the server. Now we create the response object that will be sent back to the client. The status code is set to response status code. The message is a clean generic message that is safe to expose. For details, we check the environment. If we are in development, we return the exception message because it helps us to debug. But if the application is running in production, details will be null. This prevents sensitive technical information from being exposed to users. Finally, we serialize the API error response into JSON and write it to the response body. So instead of returning a long technical exception page, our API now returns a clean and predictable JSON response. Now all we need is to register our middleware inside the HTTP pipeline. So this is done in program CS using use middleware. The position is important because we need to place it near to the top of the pipeline, right after the application is built, so it can catch exceptions from the middleware and endpoints that run after it. To test this middleware, we need to create a new temporary endpoint called test error. This endpoint simply throws an exception on purpose. Of course, we would never keep this on real production API, but it is very useful for verifying that our goal exception middleware works correctly. So when we call the endpoint from Swagger, the controller will throw an exception, and our middleware should catch it anyway. Now let's run the application and open Swagger. So here we have our new endpoint test error. Let's try it out and execute. And of course, inside the Visual Studio, we have problem here. This is a test exception from product controller. So continue, and inside of Swagger, you can see that we have 500 status code. The message is an unhandled error occurred, and this is a test exception from products controller. So after verifying that the middleware works, we need to delete and remove the test error endpoint we already added. So the test endpoint are useful during development, but we don't want to leave artificial error endpoints in our production APIs. Now let's improve our middleware even further. Right now, every exception returns 500 and internal server error. That's fine for unexpected errors, but in real applications, not every exception should be treated as a server error. For example, a key not found exception can represent a missing resource. So we can convert it to 404 not found. An argument exception can be represent an invalid input, so we can convert it to 400 bad request. And unauthorized access exception can be become 401 unauthorized. One important point, that global exception handling is mainly for unexpected errors. For normal business cases like a product not being found, or it's still okay for the controller to return not found directly, we don't need to throw exceptions for every normal condition. A good rule for this, that use normal return value for expected cases and use exceptions for unexpected failures. At this point, our API has professional global exception handling strategy. We created a custom middleware, centralized error handling, logged exceptions, returned clean JSON responses, protected production users from seeing sensitive technical details. So today we worked on error responses. That's done for this task. Run implement. So we introduced the error handling middlewares. This is done for this task too. Return status code 500, 400, and error handling strategy. Okay. Thank you for watching this tutorial. The next time we may work with the authentication and roles. Thank you. Don't forget to subscribe. In this part, we are going to make our API much more practical by adding pagination, filtering, and sorting. Right now, we call the getProducts endpoint. We return all products at once. This may work for a small dataset, but in real-world applications, this is not scalable. APIs should return data in smaller chunks and allow clients to control what they receive. So in this video, we will add support for pagination using page and page size, filtering by product name and price range, and sorting results by different fields like price or name. First, we create a DTO to present query parameters coming from the client. Instead of passing multiple parameters separately, we group them into a single object. This makes the code cleaner and easier to extend. We define page and size for pagination. Search will be used to filter by product name. Min price and max price allow filtering by price range. Sort by defines which field we sort on, and descending controls the sorting direction. Now we update the service interface. Instead of returning just a list of products, we return a tuple containing data and the total count. The total count is important because when using pagination, the client needs to know how many total records exist to calculate the number of pages. We start by converting the products table into an iQueryable. This is very important because it allows us to build the query step by step. Instead of executing immediately, the query will be running when the call to list is synced later. Next, we apply filtering by product name. If the client provides a search term, we filter products where the name contains that term. This allows simple text search functionality. So, now we add filtering by price range. If min price is provided, we only keep products with a price greater than or equal to that value. If max price is provided, we keep products with a price less than or equal to that value. This allows client to search for products within a specific budget. Before applying pagination, we can count the total numbers of records. This is very important because pagination reduces the numbers of returned items, but the client still needs to know the total number of matching results. Now we apply sorting. We use a switch expression based on the sort by parameter. If the client asks to sort by price or name, we apply the corresponding ordering. We also support ascending and descending order using the descending flag. If no sorting is specified, we default the sorting by ID. Finally, we apply pagination. Skip tells the database how many records to ignore, and take defines how many records to return. This ensures that our API only returns a small subset of data instead of the entire dataset. After retrieving the data, we map the product entities into product DTOs object using the automapper. We can return both of the data and the total count as a tuple. Now we update the controller. We use the from key attribute to bind the query parameters from the URL to our product query parameters object. Then we call the service and receive both of the data and the total count. Finally, we return a clean response that includes the data, the total count, current page, and page size. Now let's test the endpoint in Swagger. So API products. So here we can see that the page size, search, min, and max price sorting by already added to our controller. So let's try it out. So the page page 1, page size, for example 4. For the search, we can search for PC, and sorting by we can add true. So execute, and here we can find that we have only one PC and total count equal to 1, page 1, and page size equal to 4. So here we can delete this and execute again, and here we can find that he is returning 4 elements and the sorting with the term is already working. At this point, our API is more powerful. We added pagination, filtering, and sorting, which are essential features for handling large dataset in real-world application. So for the tasks, sorting already done, text cap, we did that, filtering, and pagination. In this part, we are going to add authentication to our ASP.NET Core e-commerce API using JWT tokens. So far, our API allows anyone to call the product endpoints. That's fine for learning CRUD, validation, services, and pagination, but in a real-world e-commerce application, we need to know who the user is. Later, when we add the carts and orders, each user must have their own cart and their own order history. To solve this, we will create a registration endpoint, a login endpoint, a hash user passwords securely, generate JWT token, and use that token to access protected endpoints. First, we install the JWT bearer authentication package. This package allows ASP.NET Core to read JWT tokens from incoming requests, validate them, and identify the authenticated user. Now we add JWT settings to app settings.json. The key is used to sign the tokens, the issuer represents the application that creates the token, and the audience represents the client allowed to use the token. So we also define an expiration time, so tokens are not valid forever. Now we create a user model. This represents users in our database. We store a full name, email, password hash, role, and creation date. Note that we do not store the raw password, we only store a hashed version, which is much safer. After creating a user model, we register it inside app.db context by adding user db set. Donc this tells Entity Framework Core to create a users table inside the database. So now we create 3 DTOs. Register DTO is used when a new user creates an account. Login DTO is used when an existing user logs in, and the auth response DTO is used to return the generated JWT token to the client along the same basic user information. So next we create the authentication service interface. This interface defines 2 operations, register async and login async. Both return auth response DTO if the operation succeeds, null if something else fails. Now we implement the auth service. This class contains the real authentication logic. In register async, we first check if the email already exists. If it does, we return null. If the email is available, we create a new user and hash the password using bcrypt. So this is very important because we never store raw passwords in the database. So in order to save hashed password, we need to install bcrypt.net next. Bcrypt is commonly used for password hashing because it's designed to be slow and resistant to brute force attacks. So this is much safer than storing plain text passwords. After saving the user, we generate a JWT token and return it to the client. In login async, we search for the user by email. If the user does not exist, we return null. Then we verify the password using bcrypt. If the password is invalid, we return null. If everything is correct, we generate a new token using the JWT token. Finally, the method generate GW token creates the token using claims, a secret key, issuer, audience, expiration time, and signing the credentials. Now we register auth service and dependency injection container. We use add scoped because the service depends on app DB context, and DB context is also scoped per request. So this allows us to inject the iAuth service into the auth controller. Now we configure JWT authentication. This tells ASP.NET Core how to validate incoming tokens. So we specify that the default authentication schema is JWT bearer. Then we configure validation rules. The API will validate the issuer, the audience, the expiration date, and the signing key. In the middleware pipeline, we add authorization and authentication because use authorization, the order matters. Authentication identifies the user, and authorization decided what the user is allowed to access. Now we create the auth controller. This controller exposes two endpoints, register and login. the register endpoint sends the register DTO to the auth service. If the email already exists, we return bad request. Otherwise, we return the token. And for the login endpoint, it sends the login DTO to the auth service. If the credentials are valid, we return unauthorized. If they are valid, so we return GWT token. Now let's create the add migration. So add migration, and we can call it add users table. Okay, we had a little problem with the package automapper. Okay, we go to the install it, and here we can find that we are already using a deprecated package, so we can use 12. And now inside the CS project, we are using no-warn just to continue with the tutorial, and next we will find a better solution with the deprecated packages. So now we update the database. We already added the migration. Okay, all is good. Okay, inside the database we have the products table, and if we refresh we can find the users table, and we can find all the columns we already added. So the ID, the full name, the email, the password, the role, and the created that. Now we protect some product endpoints using the authorize attribute inside our controller. Here, for now we are not modifying the get endpoint, but for the post he needs to be authorized, and for the put, in order to be able to update or make modification on one product, he needs to be authorized admin or something like that, and for the delete. So for now we leave get endpoints public because customers should be able to browse products without logging, but modifying products should be require an authentication. So before we proceed, don't forget to add await on the register endpoint. So now let's start the application and let's test the authentication controller. We can start with the register. Okay. Inside Swagger, we find that 2 endpoints on the authentication controller has been added. For the post, for the register, we need the full name, an email, and the password. So here we can use John Doe. We give an email and the password, pass, and when we execute, and here we got the token. So with an email and user role. And if we check inside the database for the users, we can find that there is a new user has been added on this time. And for the password, because we are using a hashed password, we can find that the password is already secured and hashed. And now what we can do, we can add new product without being authenticated. So the expected result is we get a problem for the authentication. So we need to create a new element, so of type PC, good PC, and we don't need the price or stock, we just execute. And here we have a problem with the authenticated bearer. So we have a problem, we can't add new elements, we can't modify them or delete them. We need authentication. So for now we have implemented the core GWT authentication flow. So users can now register, log in, and receive GWT token from the API. But right now testing protected endpoints is still very convenient. So we can generate a token, but Swagger does not yet know how to send the token without our requests. So in this part, we are going to configure Swagger to support GWT authorization and authentication. So we will add the authorize button, paste our token inside Swagger, into Swagger, and then we use it to call protected endpoints directly from the Swagger UI. So all we need to do is to update this. Instead of adding the Swagger gen, we need to make some options. So options, with a lowercase o, and inside of it, so options dot swagger swagger doc. So this is the documentation. I'm going to choose the v1 and new open API info. Okay. So we need to define a title. So let's call it e-commerce app API, and then we need the version. So it's going to be v1. Then we need to define a description API, for example, .NET Core e-commerce API. And now we need to add another options for the add security definition, and we need to define the bearer, and we need to define another open API, open API security schema. Okay. And here we need to define a name. So, and for the name we need authorization. We need the type, security schema type dot HTTP, And for the schema, we need to use bearer and bearer format equal gwt and n parameters location, and we got the header, and we need a description. So we need to enter your gwt token here. And here we need to define another options that add security, the requirement, and for the requirement open API security requirement. Okay. And here we need to define a new open API security schema. Reference equal to new open API reference so of type reference type, we need security schema, and for the ID of type string. Next, all we need to do is to verify the middleware order, so authentication, authorization. So authentication must become before authorization. Authentication reads the token and it identifies the user. Authorization then checks whether the user is allowed to access the endpoint. So if we put use authorization before use authentication, the API would try to authorize a user before knowing who the user is, so which can cause protected endpoints to fail. Now let's run the application and open Swagger. At the top of the Swagger page, we should see the authorize button. This button allows us to provide the gwt token once, and Swagger will automatically include it in future requests to protected endpoints. Next, we log in using the user we created earlier. If the credentials are valid, the API returns a gwt token. We copy this token because we will use it to authorize Swagger. Now I click on the authorize button in Swagger inside of the value field. I paste the bear, then space, then the token. After clicking authorize, the Swagger stores this value and will send it to the authorization header for protected requests. Now we test the same protected endpoint again, but this time using Swagger includes the GWT token in the request. The API accepts the request and returns 201 created. This proves that the authentication is working correctly from the end to end. At this point, Swagger is fully configured to work with the GWT authentication. We can register users, log in, copy the token, authorize Swagger, and test protected endpoints directly from the browser. So this is a major milestone because API now supports the real authentication workflow. So in this tutorial, we finished this task: implement GWT tokens, configure the tokens, add roles, we stored the hashed passwords, and the identity integration. So in the next tutorial we may work with the other controllers, adding the card system and the order system. Thank you. In the previous part we added GWT authentication to our API. Users can now register, log in, receive a token, and use the token in Swagger to access protected endpoints. But authentication only answers one question: who is the user? In a real application, we also need authorization, which answers another question: what is the user allowed to do? In this video, we'll add role-based authorization. Regular users can be browse product, but only admins will be allowed to create, update, or delete products. This is exactly the kind of security rule we need in this app. So first we need to confirm that our user model already had a role property. By default, new users will have the user role. Later we will create or update admin user manually for testing. So next, we make sure that the role is included inside the GWT token. This is important because ASP.NET Core reads the role from the token when checking role-based authorization rules. Now we update our product endpoints. In the last tutorial, we used authorize to require any logged in user. So now we make sure that the role is stricter by using authorize with roles equal to admin. This means the user must be authenticated and must also have the admin role. If the user is not logged in, the API returns 401 unauthorized. And we leave get endpoints public because customers should be able to browse products without logging in. This is common in e-commerce applications. Reading products is public, but changing the product is restricted to administrators. Now for testing, we need one admin user. So the simplest way at this stage, to update one existing user. So we can make an update inside the database. We can work with this one. It's updated, and here we have an admin. After changing the role in the database, we must log in again. So log in, try it out, and we can work with mark at mark. We execute, and here we got the token. Authorize, paste, authorized, and now we can for the product API, for example, we can add a new product. we can have a mouse. Laser mouse for $40, and we have 10. Execute. And here a mouse is added, and inside the database we can select all the products and we can find our mouse already added. At this point, our API supports role-based authorization. Normal users can browse products, but only admin can create, update, and delete them. So this is a very big step for to build an e-commerce backend, because security is no longer only about logging in. We now control what each type of users is allowed to do. So in the next part, we continue building the system where the authenticated users will be able to add products to their cart, update quantities, and prepare it for checkout. In this part, we are going to build one of the most important features in any e-commerce application, the shopping cart. So far, we have products, authentication, GWT tokens, role-based authorization, validation services, and a clean API structure. But now we need to connect products to real users. The cart system allows an authenticated user to add products to their personal cart, view cart items, update quantities, and remove items. This is also the foundation of the next big feature, orders and checkout. So by the end of this course, we are going to terminate the cart system fully from scratch. First, we create the cart entity. A cart belongs to one user. So we store the user ID. We also define a navigation property to the user entity. The items property represents all products currently inside the cart. One cart can contain multiple cart items. Next, we create the cart entity. This represents a single product inside the cart. Each cart item belongs to one cart and points to the one product. We also store the quantity because the user may add more than one unit of the same product. Now we register both entities inside AppDB context. This tells Entity Framework core that we want tables for carts and cart items. Once we create a migration, Entity Framework will generate the database schema for these new tables. Now we create DTOs for the cart features. Add to cart DTO is used when a user adds the products to the cart. It contains the product ID and quantity. Update cart item DTO is used when the user changes the quantity of an existing item. Cart item DTO represents one item in the cart response. It includes product information, quantity, and the calculated total. Cart DTO represents the complete cart, including all items and all the total price. Because we already use Fluent validation, we also add validation for cart requests. The product ID must be greater than 0 and quantity must also be greater than 0. This prevents invalid cart operations like adding a product with quantity 0 or a negative value. Now we update AutoMapper. For cart item, we map product name and price for the product related product entity. This lets the API returns useful product information inside the cart response. For cart, we map the cart ID and the list of items. Next, we create the cart service interface. The service exposes 4 operations: get the current user cart, add a product to the cart, and update quantity of an item, and remove it from the cart. So every method receives a user ID. This is very important because each authenticated user should only access to their own cart. Now register card service and dependency injection. So this allows us to inject iCard service into the card controller, just like we did with product and authentication services. Now we create the card controller. The entire controller is protected with authorize, which means only logged in users can access card endpoints. Inside each action, we read the current ID user ID from the GWT token using claims type name identifier. This is what connects the card to the authenticated user. So the controller exposes endpoint to get the card, add an item, update item quantity, and remove the element from the item from the card. Because we added two new entities, we create a new migration called add card table. So add migration, we call it add card tables. So this is where we create the cards and card items table in SQL Server. Then we apply the migration using update DB context, update database. Now inside the database, so the database is e-commerce app, tables, and we can find that the cart and carts items is added to the database. Now let's test the application. So inside Swagger, so here we have all the cart APIs, all the cart endpoints we already added. So we start with the login. We copy the token. Inside authorize, we paste it. We are logged. Now inside the database we have two products with ID 9 and 10. So here if we try to add an element to the cart, so product ID 9 with 3 elements. Execute. and here the product is added. And here inside database we have 5, the user 5, and the ID is 1. And for the cart items we have product 9 and quantity 3 with the cart ID 1. Now let's test the get API, get cart, try it out. And here we got the cart ID with the product 9, keyboard with the price, quantity and total. So everything is working fine. At this point, our e-commerce API has real shopping cart system. Each authenticated user can manage their own cart securely with the JWT authentication. So today we finished working with manage cart actions. In this part, we are going to build the order system for our e-commerce API. Until now, users can browse products, authenticate with JWT, manage their cart, and add products to it. But the cart is not the final step. So in this video, we will convert the authenticated user's cart into a real order. We will create order and order item entities, define order DTOs, build the order service, expose order endpoints, and make sure that each user can only access their own orders. First, we create an order status enum. This represents the life cycle of an order. So when an order is created, it starts as pending. Later we can move it to paid, shipped, delivered, or canceled. Now we create the order entity. An order belongs to a user. So we store the user ID and define the navigation property to user. We also store the creation date, the order status, and the total amount and the list of order items. Next, we create order item. This represents one product inside an order. Note that we store product name and unit price directly inside the order item. This is very important because product information may change later, but the order should preserve the price and name at the time of purchase. Now we register orders and orders items inside AppDB context. This tells Entity Framework Core that to create database tables for our order system. Now we create the DTOs returned by the API. Order item DTO represents each item in the order, and order DTO represents the full order response. This keeps our API response clean and avoids exposing database entities directly. Next, we update AutoMapper. We add mappings from order item to order item DTO and from order to order DTO. Since the property names match, AutoMapper can handle most of the mapping automatically. Now we create the order service interface. It exposes 4 operations: check out the current cart, get the authenticated user's orders, get all orders for admins, and update the order status. Now we implement the order service. The most important method is checkout async. So it loads the user's cart with the cart items and related products. If the cart is empty, we throw an exception. Then we create a new order from the cart item. We copy the product name and price into order item, so the order keeps a historical snapshot. After calculating the total amount, we save the order and remove the cart item. So this means after checkout, the cart becomes empty and the user has a real order. Now we register order service and dependency injection. This allows us to inject iOrder service into the orders controller. Now we create the orders controller. The whole controller is protected because orders belong to authenticated users. The checkout endpoint converts the user's cart into an order. The My Orders endpoint returns only the order of the authenticated user. Admin endpoints allow administrators to view all orders and update order status. Because we added new entities, we create migration called add the order tables and apply it to the database. So we do add migration add order table. Once it's done, we update the database. Now we verify the database on tables, and we can find that our order items has been added and orders has been added too. Now we test the full flow in Swagger. So we first start by logging in. We copy the token and paste it here, authorize. So we verify the card. So get execute. So our user already has a card. And now inside the orders, we can call the checkout, execute. So he found one element inside of it, so the code status is 200. And now we can call the get cart, execute, and the cart is already empty. So now at this point, our e-commerce API has a complete cart to order flow. Users can add products to their cart, check out, and view their order history. So admins can also view all orders and update order status. So now for the order, process order, this is done. In this part, we are going to add professional logging to our ASP.NET Core API using Serilog. So far, our API has a clean structure, validation, authentication, authorization, services, pagination, and global exception handling. But in real production systems, it's not enough. For the API to work, we also need to understand what is happening inside the application. So logging helps us track requests, detect errors, debug issues, and monitor application behavior over time. Instead of relying only on the console output provided by ASP.NET Core, we will configure Serilog, which gives us structured logs, better formatting, and the ability to write logs to files. Okay, now let's start by adding some packages. We start with the Serilog packages. Serilog ASP.NET Core integrates the Serilog with ASP.NET. This console sync writes logs to the console, and the file sync allows us to store logs inside files, which is very useful for debugging and production monitoring. Now we configure Serilog at the very beginning of program.cs. This is very important because we want logging to start as early as possible when the application starts. We set the minimum level to information, which means Serilog will capture informational messages, warnings, errors, and critical logs. Then we add two outputs, the console and the file. The file path uses logs.txt, and the rolling interval is set to day. This means Serilog will create a new log file every day. Next, we enable Serilog request logging. This middleware automatically logs HTTP requests, including the methods, paths, status code, and execution time. This is very useful because we can now see every request that enters the API and how long it takes to process. Our global exception middleware already uses iLogger to log unhandled exception. Since we configure Serilog as the logging provider, these errors will now be captured by Serilog and written to both the console and the log files. So this is a very big improvement because every unexpected errors will be now stored and traceable inside files. So now let's add custom logs inside our service layer. ASP.NET Core allows us to inject iLogger into any service. Here we inject iLogger of product service. This gives the logger that is automatically associated with the product service class. So then we can cite the class, we can define logger, log information, retrieving products with pagination, for example. We can show how many pages, the page sizes, and how many elements we have inside of it. So now we add logs to the create product operation. Before saving, we log that a product creation was requested, and after saving, we log that the generated product ID. So this is useful because if someone creates a product, we can trace when it happened and which ID was generated. We also add warning logs for expected problems like trying to update or delete product that does not exist. This is not an application crash, so we don't log it as an error. Instead, we use a log warning because it represents something unusual but handled. Now we run the application and test different endpoints from Swagger. When we call the API, we should see logs in the console, and we should also see logs folder created in the project directory with a daily log file. This confirms that Serilog is working correctly and creating files and writing logs to multiple destinations. In this part, we are going to improve the performance of our ASP.NET Core API by adding in-memory caching. Right now, every time a client requests products, our API goes to the database, executes the query, maps the results, and returns the response. This works, but for data that does not change frequently, hitting the database every single time is not always necessary. Caching allows us to store frequently requested data temporarily in memory. So the first request will load the data from the database, but the next request can return the data directly from memory, which is much faster. First, we register the memory cache service in program.cs. ASP.NET Core provides iMemory cache out of the box, but we need to register it in the dependency injection container before using it. Once this is done, we can inject iMemory cache into our service. Now we inject iMemory cache into the product service. This is where we will use caching because service is responsible for product-related business logic. We also keep AppDB context, AutoMapper, and iLogger. The cache will help us avoid unnecessary database calls when the same data is requested repeatedly. Next, we define cache keys. A cache key is just a unique name used to store and retrieve data from memory. For the list of products, we use products. For a single product, we use a prefix followed by product ID. Using constants keeps the cache keys consistent and avoid hard-coded strings everywhere. Now we start with caching a single product by ID. First, we build the cache key using the product ID. Then we call try_get_value. If the product already exists in cache, we return it immediately without calling the database. If the product is not on cache, we load it from the database, map it to product DTO, then we start in cache. We also configure expiration. Absolute expiration means that the cache entry will expire after 5 minutes, no matter what. Sliding expiration means that the entry stays alive as long as it's accessed within 2 minutes. This gives us a balance between performance and fresh data. Caching the product list is slightly more complex because our endpoint supports pagination, filtering, and sorting. So if we used only one cache for all product lists, we could accidentally return the wrong data. For example, page 1 and page 2 should not share the same cache entry. So we built a dynamic cache that includes pages, page size, search, price filters, sorting fields, and sorting directions. This ensures that each unique query gets its own cache entry. The flow is simple. First, we check the cache. If the data exists, we return it. If not, we execute the normal database query, applying filtering, count the results, sort them, paginate them, map them to DTOs, store the result in cache, and return it. Now we need to talk about cache invalidation. When a product is created, updated, or deleted, cache data may become outdated. For a single product, we can remove the cache entry by ID. For product list, it's more complicated because we created the dynamic keys for pagination and filtering. iMemory cache does not give us simple built-in way to remove all keys by prefix. So for this beginner-friendly version, we keep list cache expiration short. Later, when we move to Redis, we will discuss more advanced cache invalidation strategies. Now we can remove product caches after write operations. When a product is updated or deleted, we remove the individual product cache. When a product is created, we log cache invalidation and rely on short expiration for list caches. This is prevent the API from serving outdated product details after changes. Now we test caching in Swagger. Call get products once. The first request should load data from the database, and then we call get products by ID. The first attempt is going to load all the element with the corresponding ID from the database. Then when we do this for the second time, we should see the message that we are loading from the cache. One important limitation of in-memory caching is that it only works inside one application instance. If the application restarts, the cache is lost. And if the API runs on multiple servers, each server has its own separate memory cache. That's why in-memory caching is great for simple applications, learning, and single server deployment. But for production systems, we need multiple instances. Via Docker, for example, we usually use a distributed cache like Redis. So in the next tutorial, we are going to implement Redis from scratch, and we are going to see how to work with this distributed databases. So for this tutorial, we finish it with caching. We already implement the entities, the orders DTO for creation, updating. For the log config, we already done this using Serilog. Define relationships, for example, the relationship between product items, and orders, and domain enums. That's done. Base entities, we already done this. So in the next tutorial, we are going to work with Redis. Don't forget to subscribe. In the last part, we implemented in-memory caching using iMemory cache. This helped us improve performance by storing frequently requested data directly in memory. In real production systems, applications often run on multiple instances. In this case, in-memory caching is not enough, because each instance has its own separate memory. In this part, we will introduce Redis, a distributed caching system. Unlike in-memory caching, Redis allows multiple application instances to share the same cache, making it ideal for scalable and production-ready systems. First, we install a Redis caching package. This package provides integration between ASP.NET Core and Redis through the iDistributed caching interface. Now we configure Redis inside the program CS. This configuration specifies the Redis server. If Redis is running locally, we use the localhost on port 6379, and the instance name is a prefix for all keys stored in Redis. Now we replace iMemory cache with iDistributed cache. Unlike iMemory cache, Redis only stores byte arrays or strings. This means we need to serialize and deserialize our objects manually using JSON. So now let's implement caching with Redis. First, we try to get the cached value using getStringAsync. If it exists, we deserialize it back into a product DTO and return it. If not, we fetch the data from the database, serialize it to JSON, and store it in Redis. Just like in memory caching, we need to invalidate cache when data changes. When a product is validated or updated, we remove it. We remove its cache entry. This ensures that future requests will fetch fresh data from the database. To use Redis locally, we run it using Docker. This command pulls the Redis image and starts a container exposing the port 6379. Once Redis is running, our API can connect to it using the configuration we defined earlier. In this last video, we are wrapping up our ASP.NET 10 backend course. Over the past videos, we didn't just build a simple API, we built a structured, scalable, and production-ready backend step by step. We started from basic CRUD API and progressively added real-world features like validation, clean architecture practices, authentication, logging, caching, and performance optimization. In this last video, we will analyze together everything we have built, explain how all pieces fit together, and show why this project is much closer to a real product system than a simple tutorial. Let's start by looking to the structure of the project. We have controllers, services, DTOs, models, data layers, and now also caching and logging integrated into the flow. Controllers are responsible only for handling HTTP requests and responses. They don't contain business logic. Services contain the business logic. This is where we interact with the database, apply rules, and handle caching. DTOs are used to control what data enters and leaves our API. This protects our domain models and keeps things clean. The DB context handles database access using Entity Framework Core. This separation is very important because it makes the code easier to maintain, test, and scale. Now let's follow a real request through the system. A client sends a request to the API, for example, a GET request to retrieve products. The request hits the controller delegates the work to the product service. Inside the service, we first check Redis cache. If the data available, we return it immediately. If not, we query the database using Entity Framework Core, map the data to DTOs using AutoMapper, and then store the result in Redis for future requests. The response is returned to the client in a clean JSON format. At this time, logging is capturing everything that happens, including cache hits, database queries, and errors. This flow is exactly what you see in real-world APIs. We also implemented GW2 authentication. Users can register and log in, and the API generates a token that must be included in secured requests. We added role-based authorization, which allows us to restrict certain endpoints to specific roles like admin or user. This ensures that only authorized users can access sensitive operations. Instead of using data annotations directly in DTOs, we introduced fluent validation. This allows us to define validation rules in separate classes, making the code cleaner and easier to maintain. Validation ensures that incoming data is correct before it reaches the business logic. We added several important performance optimizations. First, pagination to avoid loading too much data at once. then filtering and sorting to give more flexibility to clients. We also introduced caching. We started with in-memory caching, which improves performance for single instance applications. Then we upgraded to Redis, which is distributed cache suitable for scalable systems. We implemented structured logging using Serilog. This allows us to track what happens inside the application, which is essential for debugging and monitoring. We also added global exception handling using middleware. Instead of returning raw errors, the API now returns clean and consistent responses. So for now, our API includes so many features that are like a production-ready system. So we have proper architecture separation, authentication, validation, logging, caching, and performance optimization. These are exactly the components we need to get a real API ready to get to be deployed on production. So, no system is ever complete, and it's so important to understand what's missing. We don't yet have refresh tokens for authentication, which would be a very big improve security and user experience. We didn't fully split the project into a clean architecture or microservices like domain, application, and infrastructure. We also don't have background jobs, rate limiting, or advanced monitoring. These are advanced topics that we will cover in second phase. In the next phase, we can take this project even further. We can implement refresh tokens, add rate limiting, introduce background jobs, and refactor the project into a full clean architecture. If you followed along and build this project, you now have a strong understanding of how modern ASP.NET Core APIs are designed. So the next phase, we are going to see how to refactor the project to get a clean architecture project. So don't forget to subscribe and see you in the next phase.